All right, guys. Today we're going to talk about antiderivatives, or section 4.9. And it really is exactly what you think it is. It's the opposite of taking a derivative. And what it helps us to do is, let's say we're given some function f prime of x. We have f prime of x, and I need to get to f of x. So this process to go from f of x to f prime of x is called taking the derivative. So this right here, to go from f prime of x to f of x, is the antiderivative. And we're going to learn some techniques today to help us get that done. Um, so the first thing that we're going to look at is just how to think backwards. Meaning, let's say I know that the derivative with respect to x of x is equal to 1. And so I'm feeling pretty good about that. I'm feeling okay, like I understand that one. That one feels good. But what if I wanted to say, well, if f prime of x equals 1, then what is f of x equal to? So knowing this fact, we can say, well, I know f of x is equal to 1, or f of x is equal to x. That's just thinking backwards, right? We're feeling pretty good about that one. Same thing if I say, okay, well, what about if f prime of x equals 2x? Well, I've seen this so many times after taking the derivative. I can say, well, f of x then is going to be equal to x squared. Because I know if I take the derivative of this, the 2 pops down in front and then the 1 stays there, right? So like, oh, that makes sense. Or if the derivative is equal to cosine, then the function has to be equal to sine of x. Now the derivative of cosine is negative sine, but the antiderivative of cosine is just regular sine. So don't be confused. I did take the antiderivative because I knew that the derivative of sine is just positive cosine. So we're feeling really good about, okay, we can think backwards on a few of these, right? Because some of these are going to be very straightforward. We can just understand it. But there's a problem here that when I take the derivative, what about the derivative of x plus 8? What does that equal? Well, guess what? That still equals 1. So my question is, how do I know that this antiderivative right here, asking for 1, wasn't x plus 8? Is it x or is it x plus 8? How do I know which one it's going to be? And the answer is I don't know. There's infinitely many possibilities. I could add any constant at the end of this, and you get a different equation that has the same derivative. So we call them a family of antiderivatives. So we can say, okay, I know that if it's 1, it could be x plus any constant, c. C could be 0. That's this one right here. C could be 8. That's this one here. So we know that if I have a family of antiderivatives for this one. Well, isn't that true for all of them then? Well, that is correct. It's true for every single one. So if you've had business calc 1 before in high school, or anything like that, you know that plus C is going to be critical when you are trying to do any of these things. Now, we have a notation here to say, okay, well, I want the derivative with respect to x of x right here. So this, if I see this, I know, okay, I'm taking the derivative with respect to x of x. Um, there has to be like a synonymous, not synonymous, but like a equal sign or something for our antiderivative, and there is. So what we do is we call it the integral, and it looks like this right here. We're going to call this an indefinite integral, and you'll see why later. So we say, I want the antiderivative of 1 with respect to x, or dx, right there. This equals x plus c, because I know the derivative, antiderivative of 1 is x, but it could be also any family of that, so plus c. All right, so let's go to a formal definition of this one right here. We can see that this is the antiderivative. It's just saying, hey, if I take the antiderivative of the antiderivative of the derivative, I get the regular function. Okay, family of antiderivatives. And then, so if we look at this right here, I know some of you are going to pause it back there. You shouldn't. I want to know the antiderivative of, well, first we're going to do the derivatives of all these. X squared the derivative of x cubed, the derivative of x to the 10th. So if I do this one, I can see it's 2x. I bring the exponent down in front, and then I subtract 1 right there. Well, the antiderivative of this one, or the derivative of this one, is 3x squared. And the derivative of this one is 10x to the 9th. I'm feeling really good about derivatives right now. I'm feeling like I'm a champion. But then I see something that looks like this, the antiderivative of 2x dx. And you know, oh, well, I just am learning this, I'm going to work backwards, right? The antiderivative of 3x squared dx, or the antiderivative of 10x to the 9th dx. Now I know if I take this up here, so what I need to get back to x squared, right? So what I can do is I can say, okay, well, this is going to be x squared plus c, and this one's going to be x cubed plus c, and this is going to be x to the 10th plus c. So notice right here, this 2 and this 2 are right there, this 3 and this 3 are right there, this 9 and this, this 10 and this 10 are right there. So what I can do is I can say, okay, well, if I add 1 to my exponent, so if I have 2x, I'm going to add 1 to my exponent, 2x to the 1 plus 1, and then I'm going to divide by that 1 plus 1. That gets me 2x squared divided by 2, which is just x squared. Same thing here. If I have x cubed, then I'm going to say, okay, well, this is 3x squared. I'm going to take the antiderivative of this. I'm going to add 1 to the exponent. 3x to the 2 plus 1 over 2 plus 1. That's 3x cubed over 3. So those are going to cancel out. I'm left with x cubed. Okay, so if that's the case, we're feeling pretty good. But when we have something like this, if I want to find the derivative of 8x to the 5th power, if I want to find the derivative of this, we know it's going to be 40x to the 4th. So when you have to take the antiderivative of 40x to the 4th, then we say, okay, well, what number was here beforehand when I take the antiderivative? Well, we do our process here. 40 times x times, or to the 4 plus 1 power, divided by 4 plus 1 equals, that's 40 divided by 5, which is 8, and then that's x to the 5th. And the whole family of them, because there's going to be a lot, right? So this is what we like to call the power rule of antiderivatives. And we have in our definition right here, power rule for indefinite integrals. See? If I have x to the p dx, then you take x to the p plus 1 and divide it by p plus 1 plus c, because we know that it's a family of functions. But notice right here, if it's p right there, p cannot equal negative 1. And that's true. What's cool, because then that's 1 over x. And some of us know that if we take the natural log of x, the derivative of the natural log of x, we get 1 over x. So the power rule does not apply to 1 over x because it's the natural log. Okay, so if we have this constant multiple and sum rule, so basically if I have some constant in the indefinite integral, I can just pop it right out front. Totally fine. It works every single time. Just like with derivatives, we can do the same thing with antiderivatives. Sum rule, we have this, okay, if I have the integral of f of x plus g of x, d of x is the same thing as the integral of f of x plus the integral of g of x, which helped make our derivatives so much easier to calculate. It's going to make our antiderivatives pretty easy to calculate. So here's some indefinite integrals of trig functions that we need to remember, okay? So we need to know that, like, here's the derivative side that we did, the fabulous 6 that you did, and then here's the antiderivatives of each of them. Notice that it's just the exact same thing, just kind of backwards a little bit. So what I want you to realize on some of these is, like, the antiderivative of sine is not just cosine, it's negative cosine, because the derivative of cosine is negative sine. So the negative, if we bring it out front here, then that would make it positive sine. So you have to play around with negatives when you do antiderivatives of trig functions. So getting these families of functions can be kind of annoying. So for example, if I want to find the antiderivative of 3x squared dx, but I'm trying to model something in a context, I get x cubed plus c. Now this is actually the derivative, or the function f of x equals x cubed plus c is what we just found. And sometimes you're going to be given, say, we call it an initial condition. So the initial condition is basically when I say, okay, I want the antiderivative if I know that f of, um, let's say 3 is equal to 4. So that is my initial condition where I say, okay, well, f of x equals 4 equals 3 cubed plus c. So that's 27. So I'm going to subtract 27 over, so that's negative 23 equals c. I'm feeling like, oh, okay. So if this, in order to meet this initial condition right here, then this function, the family member, I guess, that I have to choose is f of x equals x cubed minus 23. So the initial condition gives us a way to determine which family member to choose or calculate my c so that I can have the exact function that I took the derivative of to get to this to this before I took the antiderivative. Um, and it comes into play a lot in um, contextual problems. And one of our most famous contextual problems that we do is velocity, position, acceleration. Remember? So we can say, all right, well, I know to get from velocity to from position to velocity is the derivative. So velocity to position is going to be the antiderivative, and they're going to give you some initial value where the initial position is known. So then you can plug it in and get it correctly. Or likewise, I can go from the acceleration to the velocity, and they give you an initial velocity, and then you can find out the actual equation for it. It's pretty slick. You're going to do great. Working backwards for antiderivatives sometimes is a little bit more rewarding than taking the derivative even. Um, but we will go from there. And so we're actually going to talk a lot more about integrals and antiderivatives and what they can be used for and what they can mean in just, well, next week.